So week 4, we're going to start a new topic. In a way, it's a progressive journey into the delightful world of string algorithms, really real world as well. So the topic would be, I'm just setting myself up, sorry. The topic is suffix trees. We have covered suffix Burrows-Wheeler's transform last week. And Burrows-Wheeler's transform get constructed from suffix arrays. So it's a completely different kettle of fish in terms of the data structure, but then allows you to do a lot of activities that you could do on suffix trees, as well as many more that you can't do on suffix trees. So the data structure is very versatile, and it's been taught in 2004 in your second year treatment of algorithms and data structures. You've learned an algorithm, and we're going to supersede that learning, advance our learning. The unit is called Advanced Data Structures and Algorithms. So we're going to take it to its logical conclusion. So what you would be learning today, in fact, would be this an asymptotically optimal, meaning that you can't do better in complexity-wise in terms of space and time than what you learn in this lecture. There might be other algorithms that could do could achieve roughly the same complexity, but the go-to algorithm for suffix trees is Euclid's. So that's pretty much the highest watermark on this topic. And it has an advantage that if you construct a suffix tree of a string, we'll see what that means. And I think you already know from 2004, but we'll just quickly revise at the start. And then if you construct a suffix tree of a string, you can construct its suffix array by just traversing that string. So in a way, after this lecture, you not only have a linear time suffix tree construction algorithm, you also have a linear time suffix array construction algorithm. So it's kind of an advantage both ways. All right, so we'll just jump straight to some simple definitions that I'll be using throughout this lecture. You already know what a string is, so I'll try and go to the board. I'll be using the board quite a bit this lecture. So for those online, make sure you're listening in, tuning in to the board as well from time to time. So if you have a string, so let's call the string S this time, 1 to n. Everybody can see that my scribble there. So if you have a position I on that string, then one could say that the substring from, so this part is called the prefix, and that part is the suffix. No doubt about that, isn't it? 1 to I, if you have an I somewhere, 1 to I is the prefix of that string, I to n is the suffix of a string. So let's take, let's remove that for the moment. Let's take two variables now, I comma j. I to j would be a substring of the string 1 to n, correct? So if you go from si plus 1, si plus 2 all the way to sj, it would be a substring. Now we also know that 1 to j is a prefix. 1 to j is a prefix, right? So that's a prefix. Now j to I is a suffix of the prefix, correct? So prefix, suffix of the prefix. For the specific prefix 1 to I, j to I is, so I to j, so rather if you want to, I'll just flip the order just in case, so that we'll be consistent with some of the things later on. I'll call this j and call this I. So 1 to I is the prefix. I've just flipped the order. It doesn't matter how you name them. So 1 to I is the prefix. J to I is the suffix of the prefix 1 to I. If j less than or equal to I. Yeah? Is everybody clear about that? Now, in fact, I could have flipped the definition around and said that j to n is a suffix. Okay? J to n is a suffix, and j to I is the prefix of the suffix. So what am I trying to prove here or say here? A substring can be seen as a suffix of a prefix, or it can be seen as a prefix of a suffix, okay, as any substring. Okay? So that's what this slide is trying to tell you. When we talk about a substring is a prefix of a suffix or a suffix of a prefix. So right now, this region is a prefix of the suffix j to n. Now, what is a suffix tree? It's a tree that stores all suffixes of a string. Take that string AB, $, where $, is always that special character, remember? So what are the suffixes of AB, $? The original string is a suffix of itself. If you remove the first character, $, is a suffix starting at position 2. So if you number these things as 1, 2, 3, 4, 5, 6, 7, so suffix at position 1 is that one, suffix at position 2 is that one, 3, 4, 5, 6, 7, right? Is everyone clear about those definitions? Okay, so this is important. If there is something that you don't understand, this is the time to raise your hand. And recall that we talked about two different data structures. Initially, you would have been taught a trie, a retrieval tree. Do you remember what a retrieval tree is? It's basically, at least in the suffix trie is a retrieval tree of suffixes. Now, what's the data structure there? The data structure is you have a root, and if you go from the root down to any of its leaf, every edge has exactly one letter, one character labeled to it. Okay? Every edge has one letter. Can you see that? So if you go A, B, $, it will be one path from the root. So that's the root. A, B, $, and at the very end you reach leaf, and leaf is marking where this path started. This path started corresponding to suffix 1, right? Now, if you have $, so that's going to be B, go in the direction of B, next go in the direction of A, $, 2. You get to the suffix of 2. Let's take some other example, A, $, so you're still going on the same path as before A, but then, so let's actually do 3, okay? A, $, so it doesn't matter which you start. So let's say A, $, so A, $, so you've branched out from this internal node. So that's what a trie is. A trie of suffixes is a suffix trie. When you compress the suffix trie, in the sense that if you look at some of the internal nodes have only one child, isn't it? So it's just a linear path. There's no branching so there's no other branch except for if you came here, you have to keep going down one letter at a time. There's no other branch on this node, there's no other branch on this node, there's only one child below that node, right? So in which case, I can compress all these paths, A, B, $, into one substring. I can call that A, B, $, as a substring. Okay? So if you take a suffix trie, and whenever you see an internal node with only one branch below going down, then you compress it away into a substring. Rather than having an edge storing one character, you have an edge storing a substring, one or more characters. You can store one or more depending on the nature of the string. Is that clear, everyone? So if you want to look at any path here, let's say path suffix 5, $, that's BA, so that's $, okay? And what are these marks at the leaves? Remember, the marks at the leaves are always where the suffix starts, not where it ends. Okay, keep this in mind that every time you get to a leaf, you're saying that if I came to this leaf from the root, and the root is pointing to the suffix starting at a position. Okay? So whenever you look at the numbers there, so if you go, the longest one is A, B, A dollar, so that's going to be A, B, A dollar. Okay? So A, B, A dollar, and you came here, it's a leaf. Leaf is saying 1, which means that this path, A, B, A dollar, starts at position 1 in the string, because I'm counting from 1. Yeah? Okay, with that thing in mind, the only thing that you have to remember is you don't ever store the edge labels. I think I just wanted to say one more thing, just go back. So if you look at the internal nodes, the fact that every internal node with just one child below has been compressed away, can you see that every internal node has 2 or more branches? Okay, it has an arity. It's in computer science, the number of branches of a node is called arity, it's called arity. The arity of an internal node in a suffix tree is always greater than or equal to 2. Okay? Now, you never store these strings explicitly. What did we say? So every edge is basically a substring, isn't it? It's a substring of length 1 or more. But what did we say a substring was? A substring was nothing but a prefix of a suffix, or rather it starts at a point and ends at some point, right? So all I have to store are 2 numbers. It starts at position j and ends at position I. Start point, end point, or rather it starts at some start point and ends at some end point. So if you look at this suffix tree, it has 2 numbers replacing these characters. So A, B, A dollar has been replaced with 4, 7. So 4 is that start point, A, B, A dollar, so between 4 and 7 is that substring. So which means that you're not storing variable length substrings. No matter what the size of the substring, you're always storing 2 numbers, start point and end point. Sometimes I think you would have been taught this as start point and length. It doesn't matter if it's start point and length or start point or end point. It's more convenient because they're interchangeable, right? End point is start point plus length minus 1. Okay, so whether you store it as start point, end point, or start point, length, it's equivalent. You can change it to a start point, end point notation, or if you just had start point, end point, you would compute the length as end point minus start point plus 1. You can interchange them. Is everyone clear about what a suffix tree is? Okay, one last point. Look at the path here, A, B, A dollar. So A, B, A dollar. So it is pointing to the leaf starting at the suffix starting at 3. Okay, look at suffix starting at 3, A, B, A dollar. Have you spotted that, correct? Now look at what happens to the number out here. So technically, if you were going from the root to that leaf using this 2 index system along the edges, start point, end point system, you would have to say 3, 3 and then 4, 7. But then that's not what it's stored here, right? It's got 1, 1 and 4, 7. Now why does it hold? Now, if you look at what 1, 1 is, it's a substring starting at 1 and ending at 1. What is the letter there? It's A, correct? Substring starting at 1 and ending at 1 is a letter A. And then 4, 7 is substring starting at 4, ending at 7, that's A, B, A dollar. So if you combine those 2 things, it spells out the path A, B, A dollar. Except that the way you're storing it is not sort of syncing with the index of that specific path. But really, do you care about which instance of the substring it is? All it's saying is that if you go from the root to this internal node, it is spelling out. So what is a path here? So the whole path is a suffix. Intermediate paths are prefixes of suffix. What are prefixes of suffixes? They are substrings. So whenever you're traversing a suffix tree, whenever you're traversing a suffix tree from the root down to the leaf, the moment you go to the leaf, you get a full suffix. Somewhere in between, maybe to an internal node or somewhere in between an edge, because the edge have labels, right? So when you kind of go traverse somewhere in between, it is spelling out a prefix of a suffix. A prefix of a suffix is nothing but a substring, which means that it doesn't really matter what you label there as long as the characters in that path agree. The characters, not the exact number, but the characters. You're just using those numbers as a shorthand for those strings. Does that make sense? So wherever you see some of the numbers there, so AB appears out here at 4, for instance. So you can see 1, 2, 3, 7, 7. So that's the path to suffix 4. That is A, BA, dollar. So this A is pointing to that A rather than the fourth A at the position 4. That 1, 1 is saying that if you go from here to here, you're spelling out the substring A. And if you go from here to here, you're spelling out the substring BA. If you're going from here to here, you are spelling out the substring dollar. If you combine all of them, A, BA, dollar, which would be the path from the start of position 4 all the way to the end. Does that make sense? Everyone? Clear? There's no ambiguity about not understanding this, because if this is not understood, then almost the entire lecture would be sort of difficult to follow in the first instance. That's all. You could still work at it during self-study. Okay. So with that introduction, I'm just going to remember how we constructed a suffix tree in 2004. So here's a string with 6 letters, including the dollar. We started inserting suffixes explicitly one after another. So how did it go? You first start with the root, insert the first suffix. By the way, I'm writing it in that order. So if you're reading going from root to a leaf, I'm writing it as A, B, C, A, B, dollar. So it's kind of going in the natural path of the traversal from the root to the leaf, yeah? Just so that we can follow. By the way, internally, they are just 2 numbers. But visually, I'm just showing you as a path, yeah? Does that make sense? So you insert the first A, B, C, A, B, dollar, A, B, C, A, B, dollar. So I'm going from root to the leaf, okay? And then second would be B, C, A, B, dollar. Now I have to insert B, C, A, B, dollar into this. All you have to ask is, when you're inserting a suffix, an extra suffix, you're saying, do the existing suffixes in my tree, in the tree that is growing, does it share any common prefix? Do they have any commonality? Does A, B, C, A, B, dollar, and the next suffix that's coming, B, C, A, B, dollar, are there any commonalities between them? Are there any prefixes that are common between them? No, right? So that means that you have to branch off directly from the root and insert the second one. Then you repeat the process, rinse and repeat. Third one is C, A, B, dollar. Are there any commonalities between the 2 suffixes that are existing already in terms of the prefixes of those suffixes? Well, C is different from A, which is the starting of the first suffix, and B, which is the starting of the second suffix, so you'll have to branch it out as CAB dollar. Now it starts getting interesting. The next is AB dollar. Is AB dollar, does it have is it sharing any commonality with any prefix of a previous suffix? Which is suffix 1, isn't it? Suffix 1 has AB in it already. So AB dollar is sharing a prefix with the ABCAB dollar, the first one. So what you do is you have to branch that off at that way, isn't it? So you're branching off so that you only have one instance of of any prefix that is common between suffixes, because every time you go from a root to any intermediate node, it's basically a prefix of a suffix. Does that make sense? Okay, so you branch that off. Then the next would be $B. So what would happen to when you say $B? Anybody? If the next I'm inserting is $B, what would happen if I insert $B in this? It branches off at number 2 after B, correct? Absolutely. So that branches off after B. So B, one goes to $B, the other goes to the original one, B, C, A, B, $, and that's 2. Remember, these numbers are pointing to where these suffixes start, right? So every time you're putting a suffix, the leaves will store where it starts. Finally, you would have $, would be, it's not common to anything, it's a unique character, so it's that. So that you understand that construction, that's what you've done in 2004. The complexity is n squared. I'll let you figure out why it's n squared. So now the claim is that we're going from n squared to n. That's going to be an interesting exercise, right? Now, so buckle your seats. Jukkonen is a Finnish computer scientist. He came up with this paper in 1995. He came up with many algorithms in computer science. There's a beautiful edit distance algorithm by Jukkonen as well in 1991, but he's probably best known for his work on suffix trees, as Wikipedia also claims, okay? Or Google claims. Okay, use my slides as just a guide through your learning. There's lecture notes, but try and follow the intuition I'm telling you for the first time. I'm almost certainly telling you that you will never get the algorithm the first time you hear it. Okay, it is a nuanced algorithm. But the ideas are simple in that it is simple in hindsight. So you get that aha moment and I said, now I understand. There are some algorithms where you can follow the algorithm, it's simple enough, I understand. Some algorithms, what the hell is happening? And then you say, aha, I get it now. But to get that aha moment, you need to get the intuition, do the self-study, get guided by your tutors as well. So it's sort of an exercise where you'll have to work at it. But at the same time, I'll tell you that it'll be the most satisfying algorithm if you're in computer science for the right reasons, it'll be a very satisfying algorithm to master. Okay, real world as well. Okay. So what we're going to do, the agenda is that at a high level, I will break down what are the key ingredients for a Jukkonen's algorithm. Okay? I'll just name them and then we'll work out one after another. So it's really 3 broad ingredients. One is the idea of an implicit suffix tree. Okay? The idea is very simple, that you could very easily see in a few slides. You'll see what is this implicit suffix. You know what a suffix tree is? What does this extra implicit qualify? We will see that. Okay? And then the second idea would be suffix links in the suffix tree. So what is a suffix link in a suffix tree? Think of whenever you hear a suffix link, you see this as traversal shortcuts. So when you're constructing something, you don't always have to go to the root and start inserting. You could go from an internal node to another internal node as a shortcut. So essentially what you have is method of shortcutting the traversal rather than going from the root all the way down, you're starting from somewhere in between. Okay? That sort of helps you speed up. Then there are a bunch of 4 tricks that take a general idea and make it linear. And it happens fast, meaning in the sense that nothing seems to happen. Okay, I applied trick 1, yeah, okay, it doesn't change the algorithmic fate. Trick 2 it helps, but it doesn't really change the algorithmic fate. Trick 3, well, that's interesting. It seems to have improved, but doesn't seem to have changed the fate. Trick 4, whoop, you get a linear time algorithm. Okay? So it happens really fast, like magic. Okay? So 3 ideas: implicit suffix trees, shortcuts, we call suffix links, and the tricks, 4 tricks. That's what we're going to cover. If we are not through all of them this lecture, it'll spill over. It's okay, don't worry, we'll have a conversation about this, and we'll cover all of these properly. Okay, first, implicit suffix tree. So if you look at the string ABC, AB $, that's a regular suffix tree of that string. Okay, you don't have, you can sanity check it later on, but take it for granted that for that string there, you have that suffix tree for that string. So all suffixes will be there if you take a look at it in your free time. Okay. Now, what is an implicit suffix tree is that if you constructed a suffix tree without the $, how would it look? Same properties as the regular suffix tree with a $, but if you erased the $, how would it look? Now, it's almost immediately should be obvious to you that $, is important, the number of leaves. How many leaves do you see in that tree? How many leaves do you see? Is it not equal to the number of characters in the string? Now, if I erase the $, you can never guarantee that the number of leaves are same as the number of characters. Why? Is because it's $, is what's forcing, it's a unique character, it's forcing a branching out at every possible suffix, has to branch out to a leaf in a $. Okay? At some point, it has to end, an edge has to end in a $. If you look at every leaf node and look at the last character on the edge linking that leaf node, the black nodes basically, if you look at every black node and look at the last character, when I say I'm always going in this order, so A, B, C, A, B, $, A, B, C, A, B, $. So the last character is always a $, before 1. Similarly for 2, B, C, A, B, $, the last character is a $, and so on. For 3, C, A, B, $, the last character is a $. The reason why you have a always ending at a $, is because $, is unique, right? But if you did not have the $, and you constructed a suffix tree, you can see that it doesn't necessarily branch out. You could have some suffixes that are contained in a longer suffix. Okay? So do we have an example there? So if you look at A, B, C, A, B without a $, so you would have A, B, C, A, B without a $, and then if you look at the suffix 4, A, B, $, so if you look, it shared the same A, B, but it was a $, that's forcing it to split the path. But if you did not have it, you would basically have A, B, C, A, B as a just one single substring out there. So you never do this in the algorithm, but to give you a sense of how do you convert a regular to an implicit, you don't ever have to convert a regular to a implicit. In fact, what you have to do in this algorithm at the very last is convert an implicit to an explicit with no difference to the algorithm. You're just doing the algorithm, you just add one extra character and it becomes from implicit to explicit. So, but if you want to go the other way, rub out all $signs. If you took away all the $signs, that's what you would get. Now, can you see that some of the leaves have no labels on it because some of them had only one letter $. So if you remove those leaves 4, 5, and 6, which only had previously $, but now you have erased, you can remove those. You would get these. Now, and then now if you look at some of the internal nodes have only one child after you remove those empty leaves. Once you remove them, so you kind of have an internal node with only one child. If you compress the path, what you would get is CAB, BCAB, and ABCAB. So the relationship between a regular suffix tree and implicit suffix tree is essentially what would be a suffix tree if you constructed, what would be the structure of a tree if you constructed a suffix tree without the $. Does that make sense, what an implicit suffix tree means? So in this algorithm, we are only dealing with implicit suffix trees. At the very end, you add an extra $. in the same mechanics, it's like it's the same process, you just had an extra letter. We'll see what that means when the algorithm checks along. Okay, I will follow the intuition. This is for serving as your lecture notes as well. So let's see what this algorithm is trying to do. Okay. So implicit suffix tree sub I. Okay. So if you have a string 1 to n and I is some point, intermediate point between 1 and n. So remember that is a string without a dollar initially, okay? Where whatever string that comes to you, you add a dollar. If without adding a dollar, assume that string is 1 to n and it has some point I. So implicit suffix tree has so implicit suffix tree at position I has all suffixes of the prefix 1 to I. That means that 1 to I, 2 to I, 3 to I, 4 to I, all the way I to I would I'll just call it as one, a single letter. It's I to I is a single letter, isn't it? So you have a tree, an implicit suffix tree without a dollar, which contains the information of all suffixes of the prefix 1 to I. Does that make sense? Okay. Now, if I add a new letter I plus 1, okay? If I add a new letter I plus 1, do you see that by the definition of implicit suffix tree I plus 1, it contains all suffixes of the prefix 1 to I plus 1, which means it will contain an I plus 1, an I plus 1, an I plus 1. So adding one extra character, I plus 1, finally I plus 1. You understand what I'm trying to do here? It is basically this is basically a suffix of the prefix 1 to I plus 1. Suffix of the prefix 1 to I plus 1 is 2 to I plus 1, 3 to I plus 1, 4 to I plus 1, all the way to I plus 1 to I plus 1. So it is taking the implicit suffix tree at I and extending it by the character, one character, all of this. So all of this, the previous implicit suffix tree, 1 to I, 2 to I, 3 to I to I, is extended by that character, let's call that character Z, okay? Character Z at I plus 1, so let's call this character Z. You're adding that extra character into the implicit suffix tree. So you can derive the next I plus 1 implicit suffix tree by adding the character at the character Z, which is nothing but S of I plus 1. Okay? Does that make sense? You're just adding one extra piece of information into. How do we add it? We'll figure that out. But does it make sense of what the relationship between I and I plus 1 implicit suffix trees are? Okay? I'll say this again, even if it is ad nauseum. Implicit suffix tree I contains all suffixes of the prefix 1 to I. It will contain 1 to I, 2 to I, 3 to I, 4 to I to I. And you can construct the next 1 to I plus 1 by just adding one extra letter to that one extra, extending all the suffixes previously by one letter. And then finally, there's a new one that you will have to add, which is a suffix of length 1. Because I plus 1 to I plus 1 would be the new one that you have added. Okay, so if that's the algorithm, okay, I've already told you what, so I've already told you what what the relationship is and how you can get from one to another. Now, at the top level, the algorithm is trivial and a bit foolish as well. Because what it says is that if you have a string, let me just change that. So if you have a string 1 to n, start with implicit suffix tree 0, which means that let's actually do an example A, B, B, A. Okay? So I'll call I'll introduce two variables, phase and extension. Okay? So what does a phase mean? A phase is equivalent to saying which implicit suffix tree you currently have in the current iteration of the algorithm. So when you start, you don't have anything. So essentially, you only have a root node with nothing in it when you start this algorithm. So it's phase 0. Okay? Now phase 1, you will have to, it's like the, let's call the variable I as the phase. Okay? Phase 1, in phase 1, so that's 1, 2, 3, 4. I'll close the door. Okay, so 1, 2, 3, 4 is the 4 characters. In phase 1, you are trying to build an implicit suffix tree of the prefix 1 to the phase, starting from 1 to the phase. What's the phase number? 1. So which means that it's an implicit suffix tree containing one letter. Okay? So we'll basically, in phase 1, actually I'll draw it here. Phase 1, you have I had to account for all suffixes of the prefix 1 to 1, right? There's only one. I have to extend empty by one letter, A. That's what I've added. Okay? In fact, I will call that A in red so that we know what we have added. That was old. We started, all the red bits are the thing that I've added in this thing. Now, are there any other suffixes that I have to extend in this phase? I've finished everything, right? There's only phase 1, we'll learn all suffixes of the prefix 1 to 1 is just one suffix A, and that's been added. Now, let's go to the second phase, phase 2. Okay? Now, what are the suffixes from 1 to 2? So 1, always from the prefix is what the phase is pointing to. So when the phase is pointing to 2, you're dealing with all suffixes of the prefix from 1 to that phase. So the prefixes, the suffixes of that prefix AB are AB and B, isn't it? The two. So AB and B. Okay. So J can be the extension of previously A has to be extended by a single letter. Remember what we said, going from I to I plus 1, you're adding a single letter. So out here, do you agree that in phase 2, you would have R 1 that already exists. What is the new thing that's coming out here? In the first extension of the first suffix, previously you only had 1, 1. 1, 1 has to be extended by the new letter B, so you've added B there, isn't it? Now, that's been done and dusted. So what's the second extension? Well, it's actually not an extension, it's a new suffix that is every time in phase I plus 1, the I plus 1 suffix is always new. So B is a suffix. Do you see a B here? You don't see a B here, isn't it, in this implicit suffix tree? So what do you have to do? You have to add B as your new leaf, edge and a leaf out there. Does that make sense? Now, I move the phase to 3, phase 3, I equals 3. So if I have I equals 3, so that's phase 3, root. I'm drawing all the old bits in the previous implicit suffix tree in black, going into the next phase. This is what we are starting. Okay, this is the state of the implicit suffix tree in phase 2. Now, what's the string here? What's the prefix? 1 to 3. So A, B, B is my prefix. What are the suffixes of this prefix? A, B, 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 and B, isn't it? So A, B, B is adding one extra letter to previous A, B, one extra letter, correct? B, B adding one extra letter, and what's the last one? B, do I have to add anything here? The last one is B. Do I have to add B anywhere to this suffix tree? Because it's already there, so B would be a path, it exists, so you kind of don't have to do anything there. Finally, phase 4, because it's an illustrative example because it will tell something about the mechanics before we talk about the algorithm. So we'll write the same algorithm, 1, same structure, 2, the previous implicit suffix tree I'm drawing. So we have this. So at phase 4, you are looking at the prefix 1 to 4, which happens to be the full string. So 1 to 4, A, B, B, A. So that's the prefix 1 to 4. So I equals 4. What are the suffixes of that? A, B, B, A, B, B, A, B, A, and A, right? So A, B, B, A, correct? B, B, A, so J, if you look at J, J is pointing to, for A, B, B is extended by A, B, B is extended by A, B is extended by A, and then you're adding a new one, so that's what you're doing here. So the phase is I, the extension is whatever you had previous state, you're extending by a letter, okay? So A, B, B was extended by A, that's an extension 1. Extension 2 would be B, B extended by an A, so I'm going to draw it here. Third would be what? Actually, we'll just draw it a bit separated out so that we can see the operation a bit more clearly. Okay? Also B, B, A. Okay, so I've done exactly the same thing. I just spaced out the letters. So B, B, A. The third one would be B, A. So what would happen in B, A? Anybody? If I have to incorporate B, A into this implicit suffix tree, I'm starting at the root, go in the direction of B. Is there the next character is an A? Is the next character an A? No. So what do I have to do? I have to break this, isn't it? I have to create a new internal node and then have a new edge, call this A, and where does this start? What number do I have to put here? Anybody? Where does BA start? At what position? Position 3, isn't it? So you have to put 3 there. Okay? So that's done and dusted. A, do I have to do anything to incorporate A into the suffix tree? It's already there. From the root, if I start A is already there. So do nothing. So the entire Buchanan's algorithm tries to build implicit suffix trees of prefixes starting from a single letter, 1, then 2, then 3, by extending the previous suffixes by one letter. So every time you are in the prefix 1 to I, if you go to the next phase I plus 1, each suffix 1 to I extended by a single letter. That's what we have done out here. Now, I want you to keep track of what this complexity, if I had to implement, so the whole idea of suffix of Buchanan's algorithm is to implement this algorithm. If you actually did this, you could actually reason this in your self-study, that this algorithm, without any further tricks or shortcutting, runs n cubed. So it's worse than what you started off with in your 2004. If you implemented this algorithm would be n cubed algorithm. Okay, we went one step backwards. It's only one step backwards to pounce a little ahead, right? So we'll see how this seemingly dumb method of doing extensions can be sped up fast. Okay, so by the way, I have captured the algorithm on that slide. I've explained it with a figure out here. Okay, now I think the rules come next. Okay, before that, can everybody see the red color on the board? So phase 0 has no red. Phase 1, what are the red elements here? You had a leaf created, an edge to an existing internal node. So this is an internal node. Okay, root is internal. You started with an internal node. Okay, so you got what did you add in phase 1? You've added a leaf with an edge to an existing internal node. Correct? What did you do here? You did two things, right? One is you added an extra letter. Where is this letter? It's the last letter before you saw the leaf. Correct? So once you go AB, after that is basically the leaf. Are you following so far? And what did you do here? You added a new leaf and a new edge to an existing internal node. Right? So this red bits have been hung to an existing internal node with a label, right? That label letter. What did you do here? You added a letter just before the leaf again. So wherever there's a leaf, you just put a letter there, right? There was already a leaf, you put a letter. Okay? What did you do here? Already a leaf, you put a letter. Here, something more happened. Out here, you put a leaf to an existing internal node. So a leaf to an existing internal, a new leaf to an existing internal node. Here you did something extra. You had to create a new internal node and a leaf to that new internal node. Right? See that? The red bits are the new bits. Okay? And then whenever you have an existing leaf, you just add an extra letter to the edge leading into that leaf. Does that make sense? Or, I mean, have I clarified what you're seeing in red? Okay? Now, what are the types of operation? In fact, this captures everything, every type of new elements that you will have in any iteration, in any given any string of this construction, Buchanan's construction. Okay? So, because we'll give some names to it, okay? We'll just give some names and some mnemonics to it so that we can follow what types. We'll just categorize these types. So whenever I'm adding, I'm going to do it in some order, some logical order. So whenever I'm adding a letter to an edge to an existing leaf, so whenever adding a letter to an existing leaf, I'll call that leaf extension. Does that make sense? leaf extension, so it's an extension at the leaf, basically. So it's basically, that's a leaf extension, that's a leaf extension, that's a leaf extension, that's a leaf extension, that's a leaf extension. B has been extended to A, okay? And we'll call the leaf extension rule 1, okay? Rule 1 is the leaf extension. I'll actually, rule 1 is leaf extension, okay? Then rule 2 we will call whenever you create a new internal node and a new leaf that you hang off the internal node. So that's basically rule 2. Rule 2 or rule 2 regular. Regular rule 2 would be you have to create an internal node and you have to hang a new leaf to it, okay? But there is an alternative form of rule 2 where you are creating a new leaf hanging off but for an existing internal node. So that's rule 2 alternate. So rule 1 is leaf extension. We've seen leaf extensions there. We call creating a new internal node and hanging a leaf with an edge. The new leaf with a new edge is basically rule 2 regular. If you did not create a new internal node, you only created a new leaf and hung it on an older, an existing internal node, it's called rule 2 alternate. There's one more rule which you did nothing about. What rule was it? Remember what happened when you did A, extension A? You said, well, it's already there. So do nothing rule. So new internal node plus new leaf, rule 2 regular, new leaf, rule 2 alternate, no work is rule 3. I'm going to show the slides anyway, so just keep that in mind. There are basically 3 rules. Rule 2 has 2 alternative things. So that's what you see in the subsequent slide. Whenever an extension happens at the leaf, it's called a leaf extension or a extension at the leaf, or rule 1 of 3. We've seen that. I'm not going to persist what it means. I will talk about when it arises. Whenever there is, I will talk about when the situation arises. Whenever you have a new internal node, a leaf hung off the new internal node, that's called rule 2. When you are hanging an existing, so for instance, this one as well, this is rule 2 alternate. Can you see that? It's a new internal node to an existing, new leaf to an existing internal node. So that's going to be rule 2 alternate. So that's an alternate scenario of this where you're hanging certain things to an existing internal node. By the way, root is an internal node in this scheme of things. And rule thing is don't do anything. So there are many places where we did not do anything, right? So out here we did not do anything. So rule 3 is when a suffix is already contained in an existing suffix. Is that clear? Okay, one last thing I want you to focus. Whenever you created a new leaf, either through rule 2 alternate or rule 3. So there's rule 2 alternate, rule 2 regular. Okay, so rule 2 alternate or rule 2, whenever you created that, how many letters do you add to the leaf? What's the label of the leaf? You always add 1 letter, isn't it? Because when you create a new leaf, you're only, at every stage you're extending by 1 letter. The reason you have to branch off is because you have to accommodate that extra letter. Every time you create a leaf, you only have 1 letter here. Okay? Okay? Whenever you create a leaf. And whenever you create, once a leaf is created, all the things that I've created get extended by rule 1. Whenever you create a new leaf. So by the way, in this, do leaves ever disappear away in this algorithm? Do they evaporate? Is there any way that anything we said that kind of erases any leaf? It doesn't, right? Once you have a leaf, it sticks. And then whenever you're doing an extension by a letter, that leaf always will have rule 1. Okay? Keep that larger idea in mind. Okay? So 3 rules, are they clear? Are they clear what the 3 rules mean at least? Okay. Now I want to give you a much more, so this is what I call an instance-based thinking of what these rules are. But let's see when these rules happen more abstractly. Okay? How do we reason these rules more abstractly? Okay? Can I take this off, everyone? Okay? Okay, so rule 1 was leaf extension, right? So when does it happen? So let's say you have a string 1, you're in phase I, okay? You're in phase I. Or rather, your finished phase I, let's put it this way, let's do it in some consistent way. You finished phase I, that means that the next character at I plus 1, let's call that Z, is the next character at position I plus 1. That means that you have an implicit suffix tree from 1 to I already existing, so you have an implicit suffix tree that contains all paths in some form of the suffixes 1 to I, 2 to I, 3 to I, 4 to I, 5 to I, all the way to I to I. That's in your implicit suffix tree at position I. Now you have to account for this new, the I is, so your phase is now pointing to I plus 1, right? The phase is now gone from that previous position I to I plus 1. So you have to extend existing leaves by Z, right? So when does leaf extension happen is this scenario here, okay? So let's look at extension J. So extension is always pointing to some suffix J to I extended by a letter Z, correct? So if you have, is that a substring? Is that J to I a substring? Yeah, any J to I, don't doubt. So J to I is a substring. Can I call that substring alpha? If I did not see alpha anywhere, if I did not see that substring that I'm extending, remember this path always starts at the root, that suffix starts at the root of the implicit suffix tree. So you're saying, does J exist, J plus 1, J plus 2, I mean, you're not saying does it exist. You will have to find J because it's an implicit suffix tree that contains J to I. You will find J, you will have to find J plus 1, J plus 1, J plus 2. All of them would be prefixes of that suffixes, right? So the substrings. So you would basically have a path. So question is, have I seen this substring earlier? And if the answer is no, I've never seen this instance of the substring earlier, it will automatically end in a leaf. Because if you saw this alpha before, there would be a path of alpha like that, right? Because when you had J prime was your suffix, so J prime to I already existed. Okay? That means that its prefix is a substring should also exist in this tree. The fact that I haven't seen such alpha implies that when I went down alpha, I necessarily came down to a leaf. And the leaf would be pointing to J, where it started, because I've never ever seen that leaf except whenever it was created or extended at some point, created and extended. So J to I would end in a leaf, so you would see a J there. So when a new character comes, it will have to be, the character Z has to be the last character that you have extended. In fact, you saw that in that instance that we were looking at. Okay? Rule 1 appears in that scenario. Is that clear? Rule 2 regular. What was rule 2 regular? Anybody? It's time to wake up. Rule 2 regular. I'll change, keep to the colors. What was rule 2 regular? You're creating a new internal node plus new leaf, right? You're doing two things there. You have to create a new internal node and new leaf. So when does rule 2 regular appear? So it appears when you saw one or more other instances of alpha. I'm calling it one or more. There can be more as well. Okay, I'm just drawing one. Maybe I'll draw two of them. There are one or more other instances of, so you have seen alpha J to I, but there has been this substring, whatever J to I spells out, that substring spells out, you've seen it at some J prime and J double prime where these characters are less, these indexes are less than J. Earlier, because you've already processed them. And what? You've seen that, and the character that follows after these alpha are different to Z. Okay? Let's only put one character. This could be X and Y, or this could be X and X, or Y and Y, or any character, as long as that character is different from Z. So what does this mean? That means that if you have a root, there's some path okay, so this is a big tree, okay, so this is a big tree, this implicit suffix tree. So what I'm getting at is that if you went from J to I, you're spelling out, so let's call, I'm just putting J as, this is a letter at J plus 1, all the way, so let's say this is a letter K minus 1, this is letter K, I'm just putting some letters, and at some point you saw a letter at I, okay? So this path is spelling out alpha, and the next character after that is, let's say you had an X before, it would have been an X like that. Because remember, J prime to I would have a prefix which is alpha followed by an X. Alpha followed by an X. Similarly, J double prime to I would have the same alpha followed by an X if they were both the same letters. What would happen if they were different letters? X and Y? You would have a node like that, one going in the direction of X, one going in the direction of Y. Alpha X, alpha Y. Can you see that? Now, when you get, so in the regular rule, so by talking about same and different, I am compressing the reasoning of rule 2 regular and rule 2 alternate together, but we'll first focus on when does rule 2 regular, meaning when does new internal node and new leaf appear. So if you saw, every time you saw, so you saw an alpha, you're extending J to I with Z, but you already saw the substring J to I, we'll call that alpha, one or more times before, and whenever you saw that alpha, it was preceded by some letter, some same letter, x, not equal z. So if you had some same letter not equal z, then there would be no branching possible because you didn't see z. All you've seen is alpha x every time you saw an alpha previously, so there would be an alpha followed by an x. And then when you extend it by a letter z, what are you going to do? You're going to create a new internal node, call that z, and this would be j. Why? Because alpha z accounts for alpha z in this current extension, and then where does it ends in a leaf. So what is this z? This is nothing but the character at position I plus 1. You always remember, what did I say? Whenever you create a leaf, you always create a leaf with one single character. And that's always the character of your phase. Your phase, whatever the character of the phase, will be the character that you will be adding. But you have to create a new internal node because every time I saw alpha, I saw an alpha followed by the same letter. And that letter was not same as z. Does that make sense? Anybody? Anybody wants me to explain that differently? So that's what rule 2 regular is. Okay? Now, if, let's say, if I saw an instance of alpha, okay, so let's say that I saw an instance of alpha like that. X, alpha followed by an x at some position previously, alpha followed by a y some position previously, and then now I'm looking at extending j to I by the single character in phase I plus 1. I've seen alpha before, that would be the substring like that. Then you would see that before I did this extension to z, I would have actually seen a branch like this already, right? There's some path that would go, one towards x, alpha x, one towards alpha y. I would have already seen that. It would have already been in the tree. So if I then extended by z, what kind of an extension is that? So what would happen? Isn't that rule to alternate? I plus 1, and that would be j. I'm not creating a new internal node, I've just created a new leaf. So if you look at alternate, it is just a new leaf. Rule to alternate is just a new leaf, like that. It's hung off an existing internal node. So I looked at the cases where alpha never appeared, which means rule 1. Alpha appeared but with the same character, which is rule to alternate. Alpha appeared with different characters to what I'm extending, that means rule to regular and then rule to alternate. That's what we have considered. What is the remaining scenario? I have seen alpha z before. If I've seen alpha z one or more times before, what rule would it be? Anybody? Rule 3, isn't it? Do nothing, because if I see alpha z, I've already seen alpha z. So let's say that you've already seen alpha. So let's actually draw this. So that's z, some characters, some tree. When I am at j1, so I'm looking at j to I extended by z, but at j to I is spelling out this alpha. So j to I is spelling out this alpha. But then I saw in a previous instance a path that split at z, that went in the direction of z. Okay? So you can have two scenarios here where you can have alpha followed by a z already like that, or a z like that. It's already, so there's a letter somewhere in between an edge, or you're splitting that edge towards the direction of z. So if, let's say that you did not see, only you saw one instance of alpha, and every time you saw an alpha, it was with, that one instance you previously saw was with a z, it would basically be a scenario where you would have some some intermediate letters, and Z would be a letter. So J to I would be those letters, J to I followed by a Z. You would basically see, you would have seen before because you've seen that instance before, which means that it is rule 3. No work rule. Okay? So 3 things I have talked about. So rule 1, rule 2 regular, rule 2 alternate, and rule 3. Okay? And I've told you that we have reasoned it from the instance, an example. We also reasoned it from an abstract level of why you would have these 3 rules manifest. In fact, in those 3 rules, we have covered all possible ways in which you can extend something. Okay? All right, so now with that backdrop, much of the thinking, so this is an example which we already did, right? So we did the ABBA example on the board. So we talked about, sorry, let's go back. We talked about creating rule 2 alternate, rule 1, rule 2, rule 1, rule 1, rule 3. So we actually drew this on the board. We actually did this on the board. So you can go back and check this, what we have there during self-study. Now comes, so what did I say? I've covered what an implicit suffix tree is and how the algorithm works. Now let's start with how do you take this algorithm with these rules, which is seemingly running in O(n) cubed, and suddenly we now have an algorithm at the end which will run at O(n), right? So let's see how that's going to happen. So first is the notion of a suffix link. Okay? Let's see what a suffix link is. So you all know what an internal node is, right? You all know what an internal node is. Is root an internal node? Root is an internal node, yeah. Let's take 2 internal nodes and we'll label them U and V. Okay? Okay? Can you see that? So would you agree that if I have a string like that, 1 to let's say n, that defines a substring going from root to the internal node? Obviously, right? It has to, and what kind of substring would it be? So it starts at some point, okay, and ends at some point, right? Let's call this J and let's call this K. So this substring we'll call as some, so that's what a substring is, isn't it? That's what a substring means in a suffix tree. We can actually reason this from a prefix, rather than a full string. It's a substring of the prefix 1 to I, because we are doing the algorithm incrementally, I plus 1, I plus 2. Okay, so that's J, character at J, character of J plus 1, and character at K. Yeah? Everyone with me so far? I've just said what U means. U is the path, and it defines a substring in that region. Okay? Now, if I call the jth letter as character C, a single character C, I'm just going to abstract it, and everything after that as character as a substring beta. So I'm taking this long substring and breaking it down into one character followed by another substring. Okay, what is the minimum size of a substring in a path from a root to an internal node? What's in a suffix tree? What's the minimum substring size? It's 1. You can only have a substring of letter 1, right? Because that's the edge that you have. That means that C would be that letter. What would beta be in that case? null. So there was nothing if you have only one letter. So C is always a concrete letter, and beta is a substring of that substring, or suffix of that substring of length 0 or more. Okay? Can I represent any path from R to an internal node in that C beta form? So R to U can be treated as C followed by beta, isn't it? Where beta could be null or 1 or 2 or 3 letters long. Can you see that? Can everyone see that? Now, I ask you this question. So really that is C. So if I've already processed 1 to I and j to k exists in that implicit suffix tree, would I find j plus 1 to k also in that suffix tree? Is j plus 1 to k also in the suffix tree? Because remember what this implicit suffix tree is? It is a suffix tree of all, it's a suffix tree that is composed of the prefix 1 to I. All suffixes of them should be included in it. 1 to I should be there, 2 to I should be there, j to I should be there, j plus 1 to I should be there, and so on. So if j to k is a substring of j to I, j plus 1 to k has to be a substring of j plus 1 to I. So it should be there, isn't it? So this is j plus 1 all the way. So there should be a path of, let's say that there exists a path of this kind, j plus 1, j plus 2, all the way to k. Okay? So if there's a path from R to U of the form C beta, and there is a path from R to V which is of the form beta without the first character. Remember, this is j plus 1, j plus 2 to k. This is j plus 1, j plus 2 to k. The only difference between these two paths is the first letter. Okay? If you have this, then there is a suffix link. I'll draw it in red. There's a suffix link from U to V. It's directed. The longer one, the path that is one letter longer is pointing to the one that is one letter shorter than that, right? So what you see as, I showed it as j and k. In the figure it's j and k minus 1. It doesn't matter what the indexes are. If I just replace that as k minus 1, it's still the same idea, right? This substring is not from j to k, but j to k minus 1. But still the whole idea is that it's only the difference in the labels, notations, right? I just saw the figure talks about the path from j to k minus 1, but I was reasoning on the board from j to k, but they are essentially two numbers, right? They're two numbers that we have to think about. So the idea would be that if you have a path from root to an internal node which defines C beta, then you have another node that defines beta, then there's a suffix link that goes between them. So what does that mean? It means that in some extension, if you traversed from the root down to an internal node, existing internal node, and you did some extension, rule 1, rule 2, rule 3, whatever, the next time that you have to do, in the next extension, if you have done extension j to I, with some rules, the next extension would be j plus 1 to I. Rather than go all the way to the top and then say j plus 1, j plus 2, j plus 3 and so on, you can, wherever you stopped, you can jump this suffix link. You got a free ride until a certain point and do whatever is remaining. Okay? That's the agenda of what a suffix link is. It's just shortcutting the traversal. Remember, it's n cubed, because you always have to keep going to the start of the root and then do the extensions for every prefix from 1 to I. So, however, this doesn't change the algorithmic fate. It's still going to be bad. And I told you that everything happens very quickly at the very end, but this is what a suffix link is. Everyone understand at least vaguely what a suffix link means? Okay, shortcut. Can you stare at that example and tell me that the definition of a suffix link holds? And if there is anything that you don't understand, we will take a look at it. So remember, whenever you have the suffix link is between two internal nodes, right? One internal node points to another. All you have to do is, what's the path from root to one internal node? What's the path from the root to the other internal node? And C is that if one has the path C beta, the other will have the path beta. What's the question, Piyumi? Yes, that's what we're seeing. We are actually looking at an example. Thank you. Okay, we'll reason this. I just want students to stare at it, and then we'll reason an example. What we're staring on the screen is an example. Yes?
So suffix links, are they like part of the tree, or are they some like external thing that we've said on the tree?
Great question. They would be an intrinsic part of your tree construction, implicit tree construction. So you will have, the next question is, how do you construct them? So going to go there. So while you're building the tree, you have to somehow resolve the suffix links as the tree is being built, so that you can make use of those shortcuts and get some free rides, hitch a ride from one internal node to another internal node without going all the way back to the top for the next extensions. Okay? So let's take an example of that. Let's call this internal node. Can everyone see my mouse, right? Let's call that U. What path does it define from the root? This internal node. It defines the path BA. So we said if the path is defined by a letter followed by a substring, so BA, the first letter is C, we abstracted as C beta, isn't it? If the path is C beta, and then here the character C is B and beta is A. Yeah? So if you look at, I'm just abstracting these ideas. So if R to U is BA, and in general form it's going to be C beta, where C is a character, beta is a substring. So that's C and that's beta, isn't it? Which means that whichever node has the path beta, which is nothing but this character A, will be the recipient of a suffix link from U. So take a look at this beast here, this entity here. So this is pointing to this, obviously. What's the path of this node from the root? A, isn't it? Can you see A is the path? Yeah? Can you see that A is whatever is remaining after the first letter? So this could be more letters long, okay? This is a simple example that I've shown. It could be one or more letters long, right? Beta could be 0 or more letters long, actually, to be honest, to be fully correct. So it would be, beta would be, C is one letter. So an internal node can be so an internal node should be at least, other than the root, if you ignore the root, any internal node not a root will have at least one letter as a path of the path from root to that internal node would be of size of length 1 or more. Okay? So that's sort of an example. So now take a look at this instance. If you call this U, what's the path? Path is AB. So if AB is a path, it's pointing to this, and its path is B. So C beta, C here is A, beta is B. So the path that goes from root to an internal node which spells out the beta path will receive the suffix link from this to this. Now what about if this was u, let's say now this is u, this is an internal node, what is C and what is beta here? C is A here, the path is just one letter, beta is null, nothing. There is only one letter, which means that any path from the root whose path spells out a null string will receive it. So which has to be the root, isn't it? Root to itself is null. So u pointing to R means that, so here when this was u, this was v. When this was u, this was v. When this was u, root is the v. When this is u, root is the v, because only one character, beta is null, which means that the path of root to spelling out a null would be itself. Now sometimes it's convenient in programming, it's always useful to point root to itself. Okay, so if let's say in some extension you went to the root, so it's pointing to the root, shortcut to the root, which implies that you have not saved anything, isn't it? You only save when you go from one internal node to another internal node that's not the root. Okay, so keep that in mind. Now one key point that you'll have to remember, that every internal node, okay, ignore the root for the moment, every internal node has exactly one suffix link out of it. And that's very easy to see why. It's because every internal node will spell out a path, okay, and that path can be abstracted as C beta, which means that it points to another internal node which is at beta, which is spelling out a path beta. So there's always going to be one, exactly one internal suffix link coming out of an internal node. Now root is an exception because root doesn't spell any path, right? It can receive a suffix link, but nothing goes out of it. So you can, as a mnemonic, as in a programming thing, you can point root to itself. So you can say root is a special case where it's pointing to itself. No other internal node will point to itself except the root if you implement it that way. Does that make sense? Okay. So suffix link. So I'm going slowly, even if we spill over into the next lecture, that's perfectly fine, because there's a reason why I'm going slowly. So, and then, so the key point I'm going to make now is answering the question that we asked. So this is a lot of things on this slide which will not make sense unless I explain it intuitively. So the question is, when do suffix link get created? That's a question that just came up, right? When the hell does suffix link get created? So what did I say? I said that every internal node has a suffix link out of it. Every internal node has a suffix link out of it. When you start the algorithm, what is the internal node you start with? Root, isn't it? Root is pointing to itself. Yeah, that's not a big deal. When do you create an internal node? Which rule creates an internal node? By the way, there won't be any suffix links for the leaf, only the internal nodes. Do you create an internal node for rule 1? Okay, do you create any internal node for rule 3, the last rule? Do you create any internal node for rule 2 alternate? There's only one rule where you're doing a rule 2 regular, where you're creating an internal node. Correct? Now, let's go back to that abstraction. So this is why this algorithm is tricky. It makes you understand the structure of the string. So let's take 1 to I. The new character is coming in, and we'll call the new character Z. Okay, at I plus 1. So you're finished 1 to I, implicit suffix tree, you're extending it by I plus 1. So when did we say a new internal node, when would rule 2 regular be applied? Somebody help me? Alpha Z, when will rule 2 regular be applied? So if you had one or more instances of alpha, okay, which had a different letter, so it could be alpha x, right? If you had alpha x, so x will have to split to a z. Okay? Okay, would you have a new internal node if I saw this? You would not, because it would already be a branch. So, the strategy is, how can I resolve the suffix link at the time of creation of a new internal node? If I can resolve the suffix link of a new internal node every time it's being created, then I will be safe that all the existing internal nodes have a suffix link out of it. Correct? So every internal node will have a suffix link out of it. I'm creating a new internal node in rule 2, regular, and if I can make sure that I find its partner to pair up with at the time of creation or soon after creation, if not immediately, near immediately, then whenever I see an internal node that's not new, I know it's already had its pair matched up, linked up. Does that make sense, the agenda? Okay. So if we have R, so that's J plus 1. It doesn't matter if we call it K minus 1 or K, let's call it K minus 1. If that's K minus 1, after the internal nodes K, some I, and let's assume that you saw an X and some more letters like that, okay? I'll draw it a bit more farther so that I can do some surgery. Okay? And then so this could be a tree, a bigger tree, in which I've seen alpha spell out a path like this. Okay? So J to I is already there. I saw an alpha before, and it had an X like that. Okay? Now, when Z came, what did I do? I have to create a new internal node, hang a leaf, call this J, and this letter is Z, isn't it? Alpha Z. Clear? Now, what would be the next extension after Ji extended to J? What's the very next extension you would do in this phase? After you finish Ji extended to J, so you've created something. Do you have a suffix link yet for this? You don't. Would you have a suffix link for the black one? If you had created it, if you created a suffix link almost immediately or near immediately, you could guarantee that this has a suffix link that was resolved. Okay? Let's assume that this black one's had it, and we'll see how this red one will become black, an existing one in the subsequent iteration. So let's say this one had a suffix link to it. So this one would be pointing to some node, right? That node has to be a black one too. What is the path this defines? If there's a suffix link from U to V. Brilliant. J plus 1, I'm glad you're following. J plus 2, where does it end? K minus 1, I said. Okay, K minus 1. Okay? If it was K, that would be K, whatever the variable. Okay? So, the next extension has to be j plus 1 to I extended to z, isn't it? Okay. Now, by the way, this was one single edge. This was a path. This was one single edge where I created a new, applied rule 2 regular on that edge below an existing internal node. So I'd create a new internal node, hang the leaf, but if I assume that that existing internal node had a suffix link, let's see why it will have soon. You can go from U to V. Do I get any free ride for the next extension? So next extension is j to I extended by the letter Z. Now, let's assume that that point was k minus 1. So j to k minus 1 would be spelling out that path. So would I get a free ride if I went from here to here? Yeah, I would, right? So which path? So j plus 1 to k minus 1 is a free ride. What do I have to cover? K to I. So that's whatever is remaining here, right? Whatever is remaining here needs to be covered underneath V. Okay? Now, when you cover K to I, there are only two possible scenarios, and that slide is talking about those two possible scenarios, right? There are only two possible scenarios that could happen. You either would again create a new internal node, or you will stop at so you'd either apply rule 2 in the next extension or rule 2 alternate. So you either create a new internal node and hang a leaf, or you will just hang a leaf. There are only two possibilities that can happen in the next, and we'll see why that's the case. Okay, this is alpha, alpha x, alpha z. You've created a new internal node, rule 2. If rule 2 was applied in jth extension, the two possibilities are you would apply rule 2 or rule 2 alternate in the next one, in the next, immediately next extension. Now let's see why that's the case, one by enumerating one after another. So when would you, so what does the next extension define? J plus 1 to I, right? Is this string a part of the existing part of the suffix of alpha before? What do you want to call this? Let's call it beta. So j plus 1 to I. So j is character C. J plus 1 to I is character, is the substring beta. Okay, that's what we are saying. So this is beta. And that's one single character, C, and that is beta. So alpha is nothing but C beta, right? Where the character C is at J. So would you have seen beta here as well? Okay? And would it be possible for you to see beta not as a part of alpha, but separately as well? There's nothing constraining for beta can appear elsewhere as well, right? So whenever you see beta, either separately or as a part of the existing alpha, if it always came with the same letter, X, then what would happen is that you would have a scenario like that, isn't it? So that would be beta followed by an X. Beta followed by an X, beta followed by an X, and so on, right? Wherever you saw a beta, if it's followed by an X, then what you would have to do is to apply rule 2 regular. So beta followed by a Z now. Beta followed by a Z. And what would this be pointing to? j plus 1. Because it's a leaf where the suffix starts at j plus 1. Yeah? So a scenario is when you create a new internal node, you end up creating a new internal node in the very next extension. Okay, the moment you create that, I can change the color of that to an existing internal node by pointing it to that new one. Okay? Because I know that if that path is C beta, alpha is nothing but C beta, this path is beta, there has to be a suffix link. So immediately, if I create a new internal node in jth extension, the very next extension, I can resolve it if both are rule 2 regular. Okay? You create rule 2, a new internal node only only in rule 2 regular. So if the jth extension was rule 2 regular and j plus 1 also was rule 2 regular, then I can immediately resolve the suffix link of the one that I've created previously. All I have to do is keep a pointer. I've created one previously. What happens next? Well, I've created a new one. That new one is now gets pointed to this. But hang on, what about this one? This is a new again. What do you think we should, without doing the other alternative, what do you think we should happen to this? How do you resolve this? Isn't that the same scenario as before? Because j, if you create one, j plus 1 you have resolved. If you create one in j plus 1, j plus 2 you will resolve, the next extension. If you create one in j plus 2, j plus 3 you resolve. Now, there's a catch to this thinking. This cascade of new can go on. What if you created a new internal node in the last extension of a phase? So what's the last extension of a phase? It's just one letter, isn't it? 1 to I, 2 to I, 3 to I. The last one would be I to I. Can you ever create a new internal node in the last extension? Because remember, if you create it at j, it resolves at j plus 1. If you create it in j plus 1, it resolves in j plus 2. If you create one in j plus 2, it resolves in j plus 3. So every time you create a new internal node, it's getting resolved in the next extension of that same phase. But the question to you is, what happens if you create a new internal node in the last extension of a phase? So let's say you are in phase I plus 1. The last extension of phase I plus 1 was I plus 1th character, isn't it? I plus 1 to I plus 1. Would you ever create a new internal node by putting in the suffix of one character into the implicit suffix tree? Why? Only two options: that character exists or doesn't exist. I've not seen the character before, I've seen the character before. If I've seen the character before, which rule would that be? Rule 3. If I have not seen, which rule that would be? It would be rule 2 alternate. You will be hanging it off the root without creating an internal node. So bingo. So when you have rule 2 regular created in jth extension, that rule 2 regular could trigger, so in one scenario can trigger a new internal node where once you create the new internal node, the one that you created in the j gets resolved, its pointer suffix link gets resolved. Now I told you that there's another scenario, the only other scenario where you're not creating a new internal node. So you have rule 2 in j, but rule 2 alternate out here. So rule 2 alternate happens because of this. So what's the scenario here? So if you have a y there, so I have seen one or more instances of alpha, so you could actually have alpha, even z maybe, it doesn't matter. Okay, even if it's alpha x, you could see beta y separately. So you have root some u, so j plus 1 all the way to k minus 1, k all the way to I, and then you have x Okay, let's say you have, by the way, it has to be alpha x. I should correct myself. Whenever you see one or more instances of alpha, it has to be by the same letter, not equal to z for it to be rule 2 regular. Okay, so which means that this is alpha. So alpha is nothing but c beta. C is nothing but the character at j. Beta is nothing but j plus 1 to I. Okay, and you are extending alpha with a character z. So in jth extension, you're creating this thing j with z right there. Okay, z would be the character that you have extended. So then you take a suffix link because it's an older one. It would have been resolved somehow. We're just looking at the other case where you would have a v. That would be a path that says j plus 1 all the way to k minus 1, the same path as this one except the first letter. Okay? And then you have to come to a scenario where the only other scenario that appears is that you have an internal node, existing internal node, one going towards x, other going towards y. If you can see, alpha x, you will also have a beta. So that's beta. So that's beta. So alpha x implies beta x, right? So that's beta. So beta x is already there. But you could also have beta y separately. That means that you could be a branch that way. So which means that you have rule 2 regular in jth extension and rule 2 alternate in j plus 1. How do you, so does it automatically resolve the suffix link for this one? So this path is nothing but alpha. So if I can link this as we have done before, not to the, because now we know that if this defines alpha, this defines, so alpha is nothing but c beta. This will have to define beta. That means that the one that I've created in the previous extension, the new thing that I've created in jth extension gets resolved. There are only two scenarios possible. Okay? You either if you create a new one, you're going to see a new one in the next, or you're going to see an old one in the next. And all you have to do is every time a new one is created, in the very next extension, if you resolve it, the shortcuts are done. Does that at least intuitively make sense of what we are trying to do? In which case that every time you're creating a new one, you're resolving it in the next extension, and you never ever create a new one in the last extension, which means that all internal nodes will have a suffix link as you're generating them. That is at least the agenda does it make it clear in your head? Even if the details might be still unclear? Okay. So I think everything else is essentially the set of tricks. So if you did nothing else, if you didn't apply the tricks, the algorithm looks something like this. I'll just go on for another 3 or 4 minutes, and we'll do the tricks. There are only 4 more tricks at the end. We'll do it at the start of the next lecture. Okay, this lecture always spills over because I have to be slow and try and anchor the intuition. That's the reason. Okay, so if you did nothing, so every phase you have to start at the root, go down, and then you come to a point where you are applying rule 1, rule 2, rule 3, correct? Okay, now I'm going to introduce a terminology called, and people use it in different ways, but I use it in a specific way, and I think it's useful to reason it in the way that you're being taught this, right? Because if you go online, there are a lot of variant ways of defining this terminology, but it could lead you to some potential problems if you didn't check this, if you didn't actually understand what this terminology means. So in some traversal, you have what's called an active node. Now what is an active node? It's an existing internal node whose suffix link is already there. It's not the new one that you've created in the extension, it's an existing one whose suffix link is there. And in a path, you're looking at an active node that's the deepest from the root. Why? Because it gives you the biggest saving if I shortcut a big path, right? If I have a longer the path, the greater the number of characters I save if I serve the suffix link. Because C beta, if C beta is a big one, then I'm saving on beta length, right? So you'd want to find in any traversal the deepest internal node which has a suffix link already resolved is an active node. Not the new one that you created. You create something in J, that's not the active node. It's the U, the one above. Remember we saw that we always went on a suffix link from U, which was above the new red one that we created for, so it's this one, not this one, okay? This got created in jth extension. So when you are in some extension 1, you are essentially, the active node would be the node above the leaf, right? When you're doing the extension 1, if you did nothing else, if you didn't know any other tricks, you would start with extension 1 of phase I plus 1. So what do you do in phase I plus 1? 1 to I is extended by the letter I plus 1. So you go down. If you didn't know anything else, you have to go down. And then you find out that it's actually, does it have to be a rule 1 extension always? If it's the longest suffix, 1 to I plus 1 is 1 to I extended by 1 letter. Would you ever see 1 to I before? If you had, this is what my question is. It's a long lecture, but maybe persist for a second. If I have 1 to I extended by the letter I plus 1, would I ever see this before? It's the whole thing. It's the whole 1 to I. It has to end in a leaf. The first extension has to be a leaf extension. There's no other way that you can get any other instance of alpha, because that's the longest suffix, right? That pattern, because as you're traversing, the longest pattern will have to end in a leaf. So that's what you kind of have. I'll stop right here. So active node is the deepest internal node. So that